In October 2021, a researcher published a package to the NPM registry called ua-parser-js. That name was already taken by a legitimate, widely used library with millions of weekly downloads. The researcher had taken control of the original maintainer's account. The malicious version went out as an update to the real package. Within hours, it had been installed by automated dependency update systems across thousands of projects worldwide. The package contained code that on installation harvested cryptocurrency wallets and installed a remote access tool. It had access to everything in the build environment, including every secret injected into it. That incident ended relatively quickly because it was caught and the package was pulled. The secrets it collected during the window it was active are a different question. Supply chain attacks against secrets work by inserting malicious code into a position of trust inside someone else's build or runtime environment. The attacker does not need to breach the target organization. They need to find a package the target installs, a dependency that runs during build, a plugin that executes during CI, a library loaded at runtime, and make that component theirs. Once they do, everything that component can access is theirs too. And in a software build environment, what a component can access includes environment variables, file system paths, network endpoints, and process memory. All of the places secrets live. The NPM ecosystem is the largest surface for this class of attack because of its scale, its install time execution model, and a naming system that was not designed to prevent confusion. NPM packages can execute arbitrary code at install time through lifecycle scripts that run automatically when the package is installed, before a developer has reviewed a single line of what they just downloaded. A malicious package that harvests environment variables and sends them to an external endpoint can do so before the developer who ran npm install has finished reading the terminal output. Typosquatting exploits the gap between what a developer intended to install and what a package manager actually resolved. The legitimate package is requests. The malicious package is just a little bit different. Each of those has been published to package registries at various points, banking on a developer's fingers moving faster than their attention. In 2017, a researcher demonstrated this by publishing a package called crossenv, a near-identical name to the legitimate crossenv package that was installed by hundreds of projects over several weeks. The malicious crossenv harvested environment variables from every project that installed it and sent them to a remote server. The legitimate crossenv was a development tool for setting environment variables across platforms. The irony that a tool for handling environment variables was impersonated by a package designed to steal them is instructive about how precisely targeted the attack surface is. Dependency confusion attacks operate at a different level. Most organizations maintain private package registries for internal libraries, code that should not be published publicly, but needs to be shared across teams. Dependency confusion exploits the fact that package managers, when configured naively, will prefer a public registry package over a private one if both exist under the same name. An attacker who discovers the name of an internal package through a job posting, a public error log, a leaked configuration file, can publish a package with that name to a public registry at a higher version number. Build systems configured to resolve dependencies from both the private and public registry will pull the public version, treating the higher version number as authoritative. The attacker's code now runs inside the organization's build pipeline with whatever access that pipeline has, including every secret it holds. This technique was demonstrated at scale by security researcher Alex Birsan in 2021, who successfully executed dependency confusion attacks against Apple, Microsoft, Uber, PayPal, Shopify, and dozens of other organizations, all using publicly available information to identify internal package names. None of those organizations had misconfigured their security in an obvious way. They had made a standard configuration assumption that their package manager would prefer their private packages over public ones with the same name. That turned out to be wrong in ways the package manager documentation did not prominently warn about. The GitHub Actions ecosystem introduces the same class of risk into CI pipelines specifically. Actions are reusable pipeline components published by third parties and referenced by name and version tag in workflow files. An organization's CI pipeline might reference a dozen or more third-party actions, actions that deploy to cloud environments, actions that run security scans, actions that send notifications. Each of those actions runs inside the pipeline with access to the repository, the build environment, and every secret the pipeline injects. Version tags in GitHub Actions are mutable by default. An action pinned to a tag like v2 will resolve to whatever commit that tag points to at the time the pipeline runs, not the commit it pointed to when the workflow was written. An attacker who compromises the repository of a widely used action, or who creates a new major version tag that points to malicious code, silently updates every pipeline that references it by tag. The 2020 SolarWinds compromise was not primarily a secrets theft incident, but it demonstrated the organizational dynamics that make supply chain attacks so damaging when secrets are the target. A legitimate software update, cryptographically signed by the vendor, distributed to customers who had every reason to trust it, contained attacker code that ran inside those customers' environments with the full permissions of the software being updated. The attack was successful, not because any customer did something wrong, but because the trust they extended to a vendor's signed software was exploited at the point of production. Supply chain attacks weaponize trust relationships rather than breaking them. The defense against supply chain secret exposure has several distinct layers, none of which is sufficient alone. Pinning dependencies to specific commit hashes rather than version tags prevents silent updates. A commit hash is immutable, a version tag is not. Restricting the secrets available to any given build step to only those the step requires limits what a compromised component can access. Running third-party code in isolated environments without network access prevents exfiltration, even when the code is malicious. And auditing the permissions granted to third-party actions and packages regularly, as part of the build configuration review process, surfaces the accumulated trust that builds up as pipelines grow. The trust model underneath all of this is the thing worth making explicit. Every dependency installed, every action referenced, every plugin loaded is a decision to run code written by someone else with the access the current environment provides. Most of those decisions are made once, at the moment a dependency is added, and then forgotten. The dependency stays. The access it has stays. The review of whether the code it contains is still what it was when the decision was made does not happen on any regular schedule. A software supply chain is a chain of trust relationships, each of which was established at a specific moment and has been accumulating risk ever since. The question is not whether any individual package is malicious, it is whether the total access granted to all third-party code in all build and runtime environments has ever been examined as a single surface, and whether any of those components have changed since the last time anyone looked.